Okay, so we're talking about breeding for poll, and the kind of structure of my presentation. I'm going to give a little bit of the theory of a few different aspects of breeding for poll in our two of our different breeding programs, and then talk a little bit about what we're seeing. So I'm pretty sure, looking at the list of people, most are familiar with AACo, but for anyone that isn't familiar with AACo, it's Australia's oldest continuously operating company, and we've been around for right on 200 years now. Our 200th birthday was actually a few weeks ago, depending on how you count it. So we have about 1% of Australia's land mass, which is about 6.4 million hectares, and it's all in Northern Australia, Northern Territory, and Queensland, probably. Yeah, so we have roughly 30 stations and some farms and 2 feedlots. Okay, so just a little bit about how this project came to light and why we're sharing a lot more than probably AACo has for a while publicly about our breeding programs. So we were awarded a MDC project a few years ago now, called we call it internally Health and Horns, because that's much easier to get your mouth around than the Animal Wellbeing Extension and Adoption Project. But it's really an adoption project around two challenges in extensive or in northern breeding in particular. One is how do we breed for poll while we're doing all these other things that we need to do, and also aimed at tackling a few of the reproductive diseases that are often put in the too hard basket, like trike and vibrio and pesty. But we'll talk about those ones in later seminars, and probably with people more qualified to talk about veterinary practice than geneticists like me. Okay, let's get into some of the details, and it shouldn't really be any surprise to anyone in the cattle industry that why we're looking to breed for poll. We want to try and reduce and eliminate the need for dehorning, because when we leave horns on, obviously end up with some economic loss due to mostly to bruising, but also the animals, while injuring themselves, that it's also potentially safer for our staff, and there is some consumer pressure, or likely to be more consumer pressure in the long term on the practice of dehorning in beef cattle. And why is now a good time to really get into breeding for poll, or why is it much easier than it used to be? There's an accurate test, and it's really well integrated with normal stud practice. So most studs these days will use genomics as part of their breeding program, or many studs will, and there's an integrated test that makes it quite simple to do as part of practice. So we'll just do a little bit of the really basics of poll first before we get into some real numbers from AACo's studs. So poll is a dominant gene, or P is dominant. So if we can make a double poll bull, or a bull with 2 copies of the poll allele, all his calves are going to be phenotypically polled and a proportion scurred. And I'll talk more about scurs later in the presentation. So effectively, it doesn't matter if you mate with a PP with whatever type of cow you mate it with, he'll have 100% polled calves. If you actually have a heterozygous, so a bull that phenotypically poll, he didn't have poll horns himself, but he has 1 copy of the horn gene and 1 copy of the poll. It really depends on who you mate that guy with, what the calves are going to be. So if you mate him to a horn cow, we'll get 50% will be polled and 50% will be horned. Then if we move on to the other potential combinations, when we have heterozygous cows, or cows with 1 copy of poll and 1 copy of the horn, gets just a little bit different here. We'll bring in with the pH cows will get 50% will have, and a PP bull, you get 50% of the cows will be polled and have double polled, and 50% are going to be heteropolled. pH is a little bit different. We get a little bit of a mix of everything there. So we get a quarter with double polled, a quarter horned, and half that are carrying one copy of each. So that's the basic genetic combinations that you can get if you're breeding with different styles of, or different amounts of poll bulls and cows. So let's get into what that looks like in practice in a couple of bulls. And you might notice these 3 bulls here were part of a commercial AI program, and we had the 3 bulls, and I'll use them as a case study in a couple of slides as we go through here. So bull 1, he is a peep. These are all joined to purebred poll cows, or predominantly purebred poll cows. So we can see the AACo 62 calves, and just over half of them were carrying one copy of the poll gene, and just on half were, or just over half were polled phenotypically when we looked at their heads. The next guy, very similar, half, so meeting exact expectations. And then our last guy, in an ideal world, we'd have all of the bulls that we put out, like 733 in a way, where he has 2 copies of poll, and all his calves were polled, were carrying at least one copy of the poll gene, and all of them were phenotypically polled. Now we'll get on to why it takes a long time to get all PP bulls later on, but it illustrates that, yeah, if you do get those bulls through with 2 copies of poll, you will start getting poll calves, all poll calves. Okay, so you might have noticed in there that that last slide, there was some of those progeny of the heterozygous bulls were phenotypically not polled, so that's where skers come in. So skers generally are like incompletely developed horns, and they're generally attached to the not attached, or attached only to the skin. As you can see, there's a huge variety in what they look like in practice. So many of them are like this bull on the right, the T bull, where you just have little loosely attached skers, but we also end up with very horn-like skers in a proportion of the animals. So what happens is some of these, it's hard to determine at a young age in the cradle, and many of these, or some of these, require dehorning in practice. So if we move along now, and as I said, the skers typically only happen, or mainly happen, in the males. So we'll go back and look at these 3 bulls in a little bit more detail in their male progeny. So when we look at 6022, he had 30 male calves, 14 of which were carrying at least one copy, and we found two of them happened to be dehorned. So there was 2 on there that the skers looked big enough that in the commercial operation they needed to dehorn those progeny. In the case of 7217, similar deal, but he had a larger amount of dehorning of his progeny. And then 7333, all of his progeny, or none of them, required dehorning. And that, I think this actually shows a few things here. It shows that there is quite a variation in the size of skers, and that there's likely to be a genetic component to just how big they are. Now, just one caveat here is some in the literature, or sometimes you see people talking about PP bulls not generating skers. That's not necessarily the case. I think in this case, this bull it might have just been an element of luck in that case. But what we find in practice is somewhere between 10 and 25% of heterozygous males horn-like or big enough that they are dehorned in commercial practice. Whereas the actual rate of skers, if you really dig deeply and feel the skulls, there is sort of a very high proportion will have some sort of bump or some at least little skir there, but many of them don't need to be touched and may not even be visible outside the hairline. Okay, a little bit about the genetics of skers. I touched on it in that last slide where we have sire variants in skers, which is a good indicator there's genetic variance. So traditionally in a lot of the literature, it was thought that there's actually a single gene for skir, but more recently there's some evidence in the scientific community that multiple genes were involved. So one of the things we're able to do with our database of measuring skers on yearling bulls and doing it on a large number of bulls over 2 or 3 years, we're able to actually have a look at that and see what it looked like in the AACo herds. So the way that we often look at in the genetics side is the way we generally look at this as a first pass anyway, when we're doing an analysis to see whether there's lots of genes or there's a few major genes involved, is what's called a Manhattan plot, which is this graph we've got on the left. And along the bottom we have each chromosome, and the y-axis is how important each area of that within that chromosome is. So it looks a little bit like the skyline of Manhattan. So what we're looking for here is if we have really high peaks like this one here on chromosome 12 and even this one on 9, that's an indication that some parts of the genome are much more important for skers than others. So yeah, we found 2 areas or associations where we get somewhere around 9%, but it's definitely not, we're not finding strong evidence that there's one single gene that's causing skers. So that means, yeah, so it's kind of pushing us away from that original hypothesis that there was just one gene involved. What we do see though, even though there's not one gene, it is a heritable trait. So over time, when we get more records in, it's like that we can build an EBV for this sort of trait and could potentially select bulls that have smaller skers potentially. Okay, so that was a little bit of the theory. So again, I'm going to go back into what's happened in practice, and we'll start with the Mitchell poll program. So we've been breeding Mitchells or composites in AACo for a very long time. Probably, I think the composites started in the 80s, but this is the reason the poll status from 2017 until now. So back in 2017, we were around just over 50% of the bulls were polled, and as we started testing for poll, we've slowly in the early years we slowly introduced some more and more poll bulls, and then more recently in 2019 we decided that it was time to really finish off poll and move it a bit faster. So from 2019 all the stud bulls have been PP, which led to 2 years later, all of the actual commercial bulls were at least heterozygous polled or phenotypically polled and skirred. And as you can see over the years to where we are now, we're pretty much 99% of what we're seeing is polled bulls, and we're up to sort of 60% of our Mitchell herd this year was homozygous polled. And then let's look at a more commercial example. So 3 years ago, we started pushing full cohorts of PP bulls out to one of our commercial properties, and we've been watching for the last 3 years to see how long it takes for us to start having a big impact on the poll rate at that herd. So even though we started increasing the rate of poll in the stud in 2000 let's just go back one just to get the years right. So we started having big impacts from 2021 in the stud. The females in the commercial herd are a generation behind. It also takes a generation to replace the bulls. So it took kind of nearly 3 years of putting pole bulls out for us to start getting a really big kick up in the calving rate, or in the pole rate of the calves. So you can see now on that herd we've moved from sort of 50 to 60% of what's coming through on the females are polled. Then we can see that 39% are phenotypically polled, and this percent polled here is the percent not dehorned. So it's a really clear example of how big that the rate of removing scurs are, because the amount of heterozygous poles are the same, exactly the same in the males and females. So the only difference between the males and females here is scurs that are needing to be removed in the branding process. Okay, so that's the Mitchell program. Now we'll just run through a couple of key findings in the Wagyu pole program, and there's a little bit different to the Mitchell, where we started with the Mitchell. So with the Mitchells, when we started 50% of the herd were polled, and which is quite different to the WAGs. In the WAGs, when we started this process, and there probably is some of the people involved actually on the call, where that was back in around 2017. Worldwide, there was not very many polled bulls available. So we did a search, and we really can only access a handful of polled bulls. So when you're starting from a small base like that, we obviously have a real challenge with inbreeding. We also have to, we need to manage that. We have to also understand when we've got a smaller population, it's harder we've got less selection pressure, and genetic merit can become an issue. And then I guess as the pole program rolls out, just like we saw in those Mitchells, we'll have to deal with scurs and how we handle them in the production system for quite a while. So what I've got here is just a little bit of a snapshot of the index after about 3 years or 2 years of breeding for pole, where after running some AI programs, and what we've got here is the distribution shows where the range of EBVs were for all of the horned animals. So they're in the kind of bluey grey color, and then what was gold but seems to have gone a little bit yellow, that's the index and how many polled animals were born that year. So we can see there's 2 things in this 2019 example. We've got very few poles, and you can see that they're kind of reasonably far behind where the mean index would be for the horned purebreds and full-bloods. So if let's just zoom back a little bit and look at the change over time. So we can actually see over the last 5 years, we've increased the numbers of pole year on year to some extent, although we've contracted a little bit this year. But the most important thing we can see, we've actually got starting to generate pole animals that are definitely competitive and equal in merit to the horned purebreds that we would have been breeding. Okay, so I think I'm just about to wrap up. I've got one more sort of practical example on inbreeding. So although when we're executing the breeding program, we'll be using tools like MateCell and the digital twin to help guide us. I just thought it was good to look at a couple of example bulls and why you got to be really careful when you're designing these matings from a small population. So if we look at R7333, here's our PP bull. Remember that ideally we would like them all to be like him with horns, with their horn status, but unfortunately when he's used quite heavily, or his size we use quite heavily, it's difficult to use him in a multi-site mating for those pole females because he's quite related to them, and that's what this statistic over here. So this is pretending that the whole pole cohort that was born the same year as him is in a paddock to mate with, and we find that there's 18% of what would be in that paddock is his half sister or more related. So we can't really just do a blanket mating of him or bulls like him to that polled herd. So we actually have to develop what we often are doing is developing more outcrossed pole bulls like this, the guy up the top where he is not as related, so he'll only have less than 2% of the herd, that group will he be tightly related with. And then it's interesting just to put a benchmark that the whole Wagyu herd, it started from a small population as well. So if we look at a typical full blood, they're actually quite, the average relationship with them is fairly high. So you'd find if you took that one bull in there, he would have 6% of the herd would be his half, would be his sisters. Okay, so I'll just wrap up. So I guess that's a bit of a snapshot of where we're up to with breeding for pole, practically in AACo. And one of the most important things here is it's to do it properly. To develop quality bulls is a long-term process and relies a lot of work, hard work, and a lot of time has gone into this from many other people than me. And that's a real credit to some of the people that started before me on this journey, that to put the kind of effort and amount of giving us the amount of encouragement to really push pole out into our herds. And I think lastly, skurs, I think in the short term they'll be an issue. We've got to do a little bit of work on and work with people like the universities to understand how to interact with them better. It might be we have to evaluate how we actually, which animals truly need those removed. So I think there'll be some work to do on how we actually handle the skurs as pole programs roll out. I think that's the end of my section. I'll hand over to James.
Thank you, Matt. So my name's James Copley. I'm a fair bit newer at AACo than Matt is. I've only been here for about 11 weeks now. Before that, I worked at the University of Queensland at Coffee on this digital twin project for a little while. And before that, I was a PhD student. So in my presentation today, I'll be going through the digital twin development and what we have used that twin for and what we can hopefully use it for in the future. As Matt articulated, there are some particular challenges with selecting for polled, particularly in Wagyus. Namely, the incidence of polled within the herd is starting from quite a low base. Within the full bloods, there's obviously no polled at all. Wagyu have minimal genetic diversity as it is, and that's only going to be compounded if you only select on the polled animals. And in selecting for polled, you obviously need to balance that with selection pressure for other production traits, and you also need to manage the level of inbreeding within the herd. One way of managing this, or at least modeling it, is to develop a digital twin. So a digital twin it's a term that's really been borrowed from engineering. And it's just the idea that you generate a very precise digital copy of a system or a piece of machinery, and you use that to model different scenarios very accurately. So in the context of a breeding program, it's the idea that you can predict the outcome quite accurately before executing that breeding program, before you put the bulls out and finding out what happens. What we've used the digital twin for is to measure genetic gain for polled, for production traits, and to measure the level of inbreeding. And to measure inbreeding, we've used measure runs of homozygosity. And essentially, runs of homozygosity, they're long homozygous segments within the genome that, because of their length, are assumed to come from a common ancestor. And we measure it by saying what proportion of the genome is contained within runs of homozygosity. So the higher that proportion is, the more inbred an individual is. That's the key takeaway from that. The engine room, if you like, of the digital twin we've developed is the genomic simulation software, which is a package you can use in R, and that's been developed by Kira Villiers at UQ. What this program allows you to do is it takes an input from real genotypes. So in the context of the Wagyu herd, 2,500 animals, cows, and as well as the bulls. And we have real genotypes for all of those that have been imputed up to 600K. And then this program takes those real genotypes and crosses them and generates a simulated offspring with a realistic genotype. That's essentially what that program does. So with that simulated and realistic genotype, you can then calculate breeding values for that simulated individual, or simulated offspring, I guess is what they are. You can calculate breeding values for them, you can calculate their level of inbreeding, and then you can continue to cross those simulated offspring for multiple generations subsequent to that. So that's the real core of how this digital twin works. And that's been similar methods have been previously demonstrated in crops in AACo and in other places. And there's been a new one developed for barramundi as well. A lot of the legwork, though, with the digital twin, aside from creating that genomic simulation program, which Kira did, is to take all the nuances of a breeding program into account. And this is a lot of work that Bailey Engel did before I came onto the project. So before you can create the digital twin, you need to know how your breeding program is performing and what are the base assumptions about your breeding program you want to make. What is your weaning rate? What is your joining percentage? What is your culling rate? What is your mortality rate? What is your selection intensity? How many sires are you going to select? And if it's an IVF program, how many donors are you looking to select? How many embryos are you going to get from each of those donors? You need to know all of those parameters before you can go in and make the digital twin. This schematic is, I'm not going to go through it point by point, but this is a representation of a natural service breeding program within AACo's herd. So that's been developed over time. Again, work that Bailey did, not what I did. And so you need to know all that information before you can start, but once that's integrated into the twin, you can start modeling. The other inputs you need for the digital twin are, as I mentioned, the parental genotypes, which we have. And then you also need the SNP effects for the traits that you want to select on. So we have them for polled already, but we need them for the other traits that we want to balance polled against. And so the traits in this particular case that we've been looking at are marbling, obviously very important in Wagyus, days on feed saved, that's days on feedlot saved, 400-day weight, feed intake, and mature cow weight. And so we have SNP effects for each of those traits that have been developed within AACo's internal genetic evaluation. And those 5 traits are combined into a selection index, pretty common within the industry, and that's expressed in dollar terms. Once we have all that information, what we aim to do is to answer the key question, which is what is the optimal combination of selection pressure and breeding programs to achieve a polled herd while balancing genetic gain for other traits and balancing for inbreeding. So there's a few components to that. First is polled weight. And what I'm talking about there is the different levels of selection pressure that you want to put on polled. So 0% is that you're not considering polled at all. You're only selecting on the selection index. Right up to 100% when you don't consider the selection index at all, you just consider polled. So we've modeled this, we've run this digital twin for varying levels of polled weight or selection pressure for polled, between 0 and 100%. What we've also modeled are different variations of the breeding program. So from natural service, which was the schematic I showed there before, and then also incorporating different levels of artificial insemination into the breeding program, as well as IVF or embryo transfer. This plot here, what this shows is for a natural service scenario, the genetic gain that we're going to get for the selection index. So this is not considering polled at all yet. For the selection index over a 10-year period. And we can see that, unsurprisingly, if you put 100% weight on polled, which is the orange line along the bottom there, you're not going to get any gain for the selection index. Not surprising at all. Whereas if you put no pressure on polled, 0%, that will maximize your gain for the selection index. So neither of those 2 outcomes are surprising. And the 2 results we really want to look at are the intermediate ones, 40% weighting on polled or 60% weighting. And we'll come to that in the next plot. The other thing to take away from this is then when we overlay the results from a AI or artificial insemination scenario, what we see here is that you will get more genetic gain for the selection index. And that's just a function of, well, that's why anyone does an AI program, is to get more coverage by your best size over more of your female herd. It's just spreading more of those high performance genetics and getting more calves out of them. So unsurprisingly, over a 10-year period, that's going to improve your rate of gain. And the same again for using an IVF program or an embryo transfer program. It just means that you can have more offspring from those high performing animals. The key takeaway from just those index plots is that there's a real opportunity cost of only selecting on pole. You are going to sacrifice a lot of genetic gain for other traits if you only select on pole. And that's going to, in the case of Wagyu, if you only select on pole, you're probably going to be compromising, well, you're not going to be getting the gain that you could for marbling and carcass traits, and potentially not getting the value that you should from your carcasses. This is a similar plot, but this shows the gain for polled frequency. So that's on the y-axis, so from 0 to 1. And that polled frequency, so that's within the herd, and that is the homozygous polled and the heterozygous polled animals combined. This, again, for a natural service scenario, and what we see is that over a 10-year period, we can almost get to that 100% polled within a herd, starting from a very low base. The most important point to take from this is that there's no real difference in terms of the gain or the trajectory of achieving that 100% polled between a 60% weighting and 100% weighting. I think that's a function of, within this particular herd, within AACo's scenario, starting from the base that we are, which is low polled, that there's no point in going 100% selection on polled. There just aren't enough polled animals to start with to be able to do that. So this takes us nearly back to that first plot for the selection index, showing that if we went at 60% weighting on polled, we're still going to get reasonable gain for the selection index, and we're also close to our maximum rate of gain for polled. So I think that's an important thing to take into consideration. Again, with an AI program being overlaid, we're going to get to that 100% polled a little bit faster. So as opposed to almost getting there after 10 years for natural service, we're going to get there closer to 8 to 9 year time frame using an AI program. And for IVF, we'll get there a little faster again. The key takeaway from those first two results is that there's no real point in exceeding a 60% weighting on polled in this particular herd. It's not going to get you to your destination, which is 100% polled herd, any faster really, and you're just going to be sacrificing genetic gain for other traits. What this is now is what I talked about before, which is this measure of inbreeding we're using, which is the proportion of the genome that is contained within runs of homozygosity. So on that y-axis there, the higher that value is, the higher the level of inbreeding. For the natural service breeding program, this doesn't make a huge amount of difference which polled weighting we're talking about. Yes, it's going to be higher selecting 100% on polled, but there's no enormous difference between those levels of inbreeding. What does make a difference, beg your pardon, what does make a difference is the choice of breeding program. We can see here that the inbreeding is higher than an AI program, and significantly higher again if you use an IVF breeding program. So the level of inbreeding there, that's up above 7%, and that's getting towards the sort of level that has been documented in wild species and particularly in dairy cattle as being, it's getting close to the level that you start worrying about inbreeding depression, as well as genetic defects. So that's something to keep in mind, that whilst IVF breeding programs do get you there faster, you have to manage the levels of inbreeding. It's been said about, the harder you go or the faster you go, the more careful you have to be. So IVF is certainly great technology and it can maximize your rate of genetic gain, but inbreeding does need to be taken into account. What we also wanted to demonstrate with this digital twin is that it's adaptable. It's not only about modeling AACo's Wagyu herd for polled. The genomic simulation software and the code that's been written around it can be used to model other scenarios. So we wanted to demonstrate that it's adaptable to other scenarios. And in doing that, we wanted to look at a scenario that's fairly common in the industry, which is what if you have a small herd and you're only using IVF to breed your animals? What are the outcomes from that going to be? Can you get a higher rate of genetic gain even with that small herd? And what is the impact on inbreeding likely to be? For this, I've taken that 60% weighting on polled as a baseline, just because it seemed to be optimized for AACo's herd. And then I've compared that to this smaller scenario for genetic gain and for inbreeding. So this is the genetic gain in that small herd scenario. It's the orange line there, which is a bit jagged, you can see going along the top. And that's its genetic gain over 10 years for the selection index. We can see with its higher rate of, with its higher selection intensity, it does have a higher rate of gain, even than the IVF scenario within AACo's herd, but it's not significantly higher. The same for polled. You do get to that 100% polled frequency a little faster, but not significantly so. And that comes at a significant risk of high inbreeding. So we can see if you look at the orange line is obviously for the small herd scenario, but the yellow line there, that was the IVF scenario we looked at earlier, which was getting up towards 7%. This small herd scenario is approaching 17.5%. And that is definitely within the realm of high risk for genetic defects, inbreeding depression, etc. There are some elements of this small herd scenario that potentially are a bit unrealistic. It's only drawing size and donors from within that herd. You're not bringing in outside animals, which in reality you potentially would. But this demonstrates that you really do have to do that. The key takeaway so far from the digital twin for the Wagyu herd is that achieving 100% polled herd within 10 years is definitely feasible, and that the use of IVF programs are a great tool for getting you there faster, but these will potentially result in higher rates of inbreeding, and so you do have to take that into account. For AACo's herd specifically, found that selecting, putting selection pressure beyond 60% on polled is not really worth it. You're only going to be compromising your rate of genetic gain for the selection index, and that is your production traits, without increasing your rate of polled. We'd like to do more with this digital twin. I've only been on the project for about 6 months, and it still has 2 years left to run. So we'd like to expand it to look at other things. So one example was that small herd scenario. We've established that you can use it for different production systems and different breeding programs, but we'd also like to use it to track recessive genetic conditions. So what is the risk of that, particularly in Wagyu, and what is the risk of if a new genetic condition emerges and you don't keep track of it, how many carriers are you potentially going to end up with that up to 5 to 10 years? One thing that we're definitely working on is how to integrate better management of inbreeding by using mate selection and allocation. And then there's various programs to do that, and so I won't get into them. But one assumption we're making within this digital twin is that we're always just choosing the highest indexed animals to breed from. In reality, you would probably want to, which is why we're probably seeing high rates of inbreeding. In reality, what you would want to do is to, yes, take those high performing animals, but you would also need to balance that with your inbreeding. And programs like MateCell already do that. So we'd like to integrate those sort of programs into the digital twin so that when those selection decisions are made every year, we're not just picking the highest performing animals, we're also picking animals that will, a group of sires that will manage that rate of inbreeding. We'd also like to expand this to the commercial herds. For example, what is the best way that we can use those seed stock genetics within the commercial herd to maximize the rate of genetic gain? Ultimately, would be great if this digital twin could be made into a dashboard version, where if you know all the parameters about your herd I spoke about earlier, which is your joining rate, number of cows you have, your weaning rate, and what your breeding objectives are, if you know those base assumptions and those goals, that you could go to a dashboard, enter that information in, and it would be able to tell you or indicate to you what the optimal path to achieving those breeding objectives is. So that would be the ultimate goal, but we've probably got some work to do to get there. I'd like to particularly thank Future Beef for hosting the webinar today and for Beef Central for advertising it. I'd like to thank Meat and Livestock Australia and the MLA Donor Company for funding the research. I'd like to thank AACo for providing all of the data, and I'd like to thank the University of Queensland, specifically Quaffy, for all the work that the team there have done. Particularly like to thank Bailey Engel, who's my former PhD supervisor, and for the enormous amount of work she's done on this project. Most of what I presented today is work that Bailey has really done, so thank you to her. Thank Kira Villiers for making the genomic simulation software, and Professor Ben Hayes for heading up the project. And also like to thank Dr. Gerhard Moser for the work he did.